This is Lecture 13, Introduction to Color Science, Part 1. This lecture is intended as an introduction to optical density or absorbance analyses. I want to talk about color science primarily because it is relevant as a career. So it is a branch of analytical chemistry used in industry and has its own set of terminologies that are relevant to what we are studying and getting a job eventually. And there are elements of psychophysics that are used in this type of work. So the idea overall is to make quantitative statements in the discussions and characterizations of color. What we call color is actually a stimulus. In other words, there are multiple factors that are involved in how we interpret color. So the three elements are the source of light, the object that interacts with the light, and then how the resultant, namely the light reflecting off the object or being emitted by the object, is perceived and interpreted. There are two relevant receptors, namely the eye and the brain, or a photoelectric detector or a device, say a spectrometer. The definitions are luminant mode of viewing, in which the object itself radiates, and then the object mode of viewing, in which light is reflected off or transmitted by a material. Light is, from physics, we know is electromagnetic wave. It's an oscillatory electric and magnetic field perpendicular to one another. It's a sinusoid, and one distinguishes the types of light based on the wavelength. The short wavelengths correspond to high energy, so X-rays, gamma rays, ultraviolet light, working towards a longer wavelength. The long wavelengths are low energy, the infrared, microwave, and radio waves, again progressing from short to long. And intermediary, we call the visible wavelengths, those that we can see, having those electromagnetic waves in the range of 380 to 750 nanometer wavelength, perceptible by the eye. And white light, we know it can be dispersed into different colors according to wavelength based on the refractive index. You may be familiar, or your parents may have this record album which displays the attributes of the dispersion of white light. We know that light can be generated by heat, so there's a conversion of energy. As you raise the temperature of an object, it starts to glow and give off light. As you increase the temperature of the material, the light will start to go from a dull red to a white. We call this the black body radiator. And the typical device here is shown on the left. So the circular object, the cylindrical object, is an oven powered by a supply, and you can control the temperature of the interior of the oven. To the right is what's called a spectral power distribution, and you can see that the distribution of emitted power irradiance varies according to temperature. And in this particular case, we're looking at an oven that goes from room temperature up to 1,000 degrees. And you can see that the distribution of energy starts to spread out a little bit as you go to high temperatures. Again, merging into the white light on the left and fading off into the far infrared microwave region. An incandescent light source, namely a tungsten wire, is identical to a black body radiator. The temperatures are higher, and so the spectral energy distribution or spectral radiant distribution gives you more illumination or radiance in the visible range. So the tungsten halogen lamp spectral distribution is indicated on the right in this case, and you can see that as the wattage, namely the power going through the device, the tungsten wire, increases, you get a broader spectrum. So you actually get into the UV when you get up to 1,000 watts, actually to some extent also in the 200 watts. Very little UV when you work at 45 watt. One often sees, particularly in terms of lighting, a reference to a so-called color temperature. And this is a reference to a black body radiator whose oven is at a given temperature, and the quality of light, namely the spectral power distribution that accompanies that given temperature. In the diagram at the lower right, you'll see four curves ranging from 3000 Kelvin to 7000 Kelvin, and you can see that as the temperature increases, the spectral power distribution begins to move or extend into the visible range more extensively, and you now get a more or less uniform distribution of light into the visible range as opposed to just simply the red. Furthermore, in the case of psychophysics, you're familiar with the expressions of warm versus cool light, particularly if you're a photographer, and the warm light has a more reddish quality to it, where cool light has more blue. As a result, there are standards given, namely a tungsten lamp, which has a color temperature of 2854 Kelvin, and the color temperature of normal daylight at 6500 Kelvin. And we can see that the distributions change. So the tungsten lamp has a different distribution than the solar energy at 6500. And this is actually how one determines the temperature of celestial bodies. You look at the light being emitted from the object, and you relate that to the black body radiators and what temperatures give what characteristic color. So you can see that the sun has a characteristic color temperature, 6,000 to 5,000 K. For starters, then, we want to have a standardized light source. Now, we distinguish a source, which is an object that actually exists, from an illuminant, which is a desired spectral power distribution that may or may not be realizable in a practical sense. So there are a number of standard light sources available from manufacturers, and we'll talk about these in a little bit more detail. But these can be purchased. They're usually rated by color temperature, and they have a very well-defined spectral power distribution. A few commercially available sources are illustrated here. Their spectral power distribution is indicated graphically, and then the dominance of the colors as would appear in the superimposed over the spectral power distribution to get a better idea of what these light sources do. So the traditional ones, now more or less obsolete, are the CIE source A, B, and C. So one is the incandescent light that I mentioned, the tungsten lamp, 2854 Kelvin black body radiator. Then there's the source B, which is a simulated light source that tries to replicate the noon sunlight, and that's a 4874 K black body. And then there's the source C, which is the overcast daylight, 6764 K black body. And here is the more comprehensive list, the more modern and up-to-date list. And you can see that the sources B and C are considered obsolete nowadays, but they've been changed. I mean, there's a North Sky daylight source, namely the D75, and there are others that more or less cover the obsolete B and C. I think what's happened is that a traditional black body radiator is not used so much anymore. And as we'll talk about in a slide that's coming, you can replicate these spectral power distributions by combining a tricolor. And so this is what I mean by the tricolor. You can take any arbitrary lamp indicated at the bottom of the cartoon, so a test lamp, and take any three colors. Generally, you can take primaries, red, green, and blue, LEDs, for example, and make combinations of the red, green, and blue, varying the intensity until you get a color match or a quality match to the test lamp. So what you're doing is artificially creating a spectral power distribution by combining three colors. Now remember, returning to our original statement about the color effect and the psychophysics involved. We said that there was a source which has a spectral power distribution. We have the object, the thing that we're looking at, and that has a spectral response, namely the reflectance or the absorbance of the light that is impinged or transmitted through it. And then there's the observer, which has its own characteristic spectral response. The combination of these three spectral responses or behaviors is what we call the stimulus. In other words, how we interpret a color. So the stimulus itself is actually a multiplicative property. So you have a spectral distribution associated with each portion of the stimulus process that gives you a resultant, namely how you perceive color or an instrument detects color. So if the stimulus is actually a three-component composite, then there are things that can go wrong in any stage of the stimulus process. So there are certain terminologies that are used to describe phenomena, namely things going wrong. The first of these is flare, when an object seems to have a different color when viewed by the same observer under different light sources, and metamerism, which when objects having a different spectral reflectance appear to have matching colors when viewed by the same observer under one light source, but then under a different light source they appear differently. So you can change the combination of sources, or observer for that matter, and get different types of matches. So this becomes problematic in the case of, say, industry where you're making textile dyes and you want to make sure that the stuff in the store looks the same as the consumer product when it goes home. So one of the differences between the different observers is indicated here in this cartoon. So the human eye has a sensitivity range that maxes out around 550 nanometers and spans 400 to about 750. So indicated by what looks like a kind of Gaussian curve in the middle. If you try to come up with a photoelectric device, a photomultiplier tube, which we'll describe in more detail in instrumental analysis, it has a maximum response at around 410 nanometers and then trails off as you go to higher wavelengths. The different silicon diode, however, is insensitive at around 400 and gradually increases linearly until you get to about 750. So the device you use to detect the light will impose a characteristic limitation on the interpretation. And this is where we're going to leave part one of the color science discussion.